Hello, welcome back. In this segment, I want to show you how to prove two functions are equal to each other. For example, I have an obfuscated version of some function and then an unobfuscated version of identical behavior. The goal is to prove that these two things are equal. When you call obfuscated of x, it returns some r. When you call unobfuscated of x, it returns x XOR with 92. Let's say the theorem is that these two things are equal. Okay, this one and this one are equal. In this case, I'm going to limit the x to be only an 8-bit number. You can see here it's a bitwise AND with 255, means in the end, the answer returned by R is an 8-bit number. Okay, I create a solver object, and then I'm negating the climb, right? If the negation of the climb is satisfied, that means they are not equal. On the other hand, if the negation is not satisfied, that means this is always false. That means these two things must be equal to each other. Okay, that is the rationale. Okay, we can quickly prove this now. Just say Python XOR, just a few seconds, right? We can even measure the time. Okay, on the other hand, you could also write a little for loop, go through all the numbers from 0 through 255 and prove that these two things are equal, right? By brute forcing. But this is not really brute forcing. This is more systematically performing comparison between this particular function and this particular function. This sounds like too powerful, but I will also show you now a case where you can't prove that easily. Here is an obfuscated version of something. We don't know what exactly it is, right? X, Y, Z are three numbers. And the unobfuscated is X, Y, Z, but Z is discarded, right? X plus Y. The claim is that the obfuscated version is same as unobfuscated version, similar to the previous demo. And we will see that it's going to take forever. Okay, let me try to show you first for 8-bit, right? Even for 8-bit, it's going to be intense. Now I'm trying for 8-bit. Okay, this is even slower than trying all possible 256 numbers, it seems like. You see here, it's not done. Yeah, only now it's done. So it's clearly significantly slower than the previous proof. But if you now go back to the model, right, the SMT program, and if you increase the bit vector size to 16, it's going to take forever. And 32 is going to take forever. I was told online that it will take about 5 to 6 hours. It was not able to come up with the answer. It's clearly taking time. So I'm going to just open the program and show to you one more thing, right? C3 is a very good tool, of course, but there are limitations. When you multiply two terms, when you have a nonlinear equations, what it means nonlinear is, for example, somewhere in the expression, right? If you have X and Y multiplied with each other, this is nonlinear. If the expression C has some nonlinear, it can be a problem. Okay, meaning it was not able to solve and conclude that the value returned by this expression is same as just adding the two numbers X and Y. Okay, so Z3 can be slow or not able to prove correctness all the time. So there are constraints, nonlinear constraints. Integer arithmetic is not desirable from a computability theory perspective. Therefore, oftentimes you get into traction problems. It's untractable problems. Okay, of course, for XYZ being 16-bit number, you could write a little for loop and call this for all possible XYZ, and the same here, and then check whether anywhere there is a mismatch. But what if X is a 64-bit number or even higher? Then you are going to spend a lot of time. Okay, it's not a good idea to do brute force, of course. Only for small bit vectors, you can do brute force. Okay, let's see whether any success has been made on the other terminal. Let's see. Oh, it's still running. Okay, that means Z3 is challenged by this obfuscated code as an attacker, right? If you wanted to send malware, that will be difficult to deobfuscate or unobfuscate. You wanted to make the expressions complex enough that it has some constraints that will be too difficult for a solver to solve. Okay, there are research articles that are explaining techniques to unobfuscate this code. Okay, they still use Z3 under the hood, but they do some more transformation before they call Z3 directly. Anyway, so my point is to show that you will be faced with challenges related to proving correctness. By blindly calling Z3, you cannot just assume everything will be proved. Okay, that's all. Thank you very much.